Hey guys, today we're going to talk about some basic pole loading concepts. This will be divided into two parts. Part 1 will cover the loads applied to poles due to equipment and conductors. This will include equipment like the three-phase transformer bank we've been looking at in previous videos. We'll also cover the loads that conductors place on poles in 3 different configurations, including tangent poles, angles, and dead ends. Understanding some basic concepts and terminology of pole modeling is critical to designing an overhead line that can withstand the heavy physical loads of the equipment and extreme changes in the weather. Part 2 will cover additional pole loading concepts due to that, weather. The physical loads applied to utility poles can be divided into 3 types. The first type are vertical loads. These are the loads applied to the pole in line or parallel to the center axis of the pole. We also have horizontal loads, and horizontal loads can be classified in 2 different ways. Longitudinal loads, which act in the direction of the attached conductors, and transverse loads, which act in the direction perpendicular to the conductors. We'll be looking at all 3 of these and how they're evaluated. Before we get started, let's look at a utility pole for a moment. From the ground, utility poles might appear to be cylindrical in shape, but they're not. They're actually tapered cylinders. The base of the pole has a much larger diameter than the tip of the pole. Utility poles can be made from a variety of materials. The most common are wood poles made from southern pine, Douglas fir, red pine, ponderosa pine, western red cedar, and northern white cedar. Poles are also made from steel, fiberglass, and sometimes concrete. Because of the variety of materials that poles are made from, and the various sizes and applications with which they're used, the American National Standards Institute has created a set of uniform standards regarding pole classifications. The most common class of pole used in overhead electric distribution are classes 5 through 1, and also H1 and sometimes H2. These are listed in order of overall strength, H2 being the strongest pole on the list, down to class 5, which is much less so. For example, the standards for a 50-foot pole will identify the pole class. They'll usually show the minimum required diameter at the tip of the pole and the diameter at a point 6 feet from the butt of the pole. They'll show the maximum allowable tip load. This is the weight that can be supported by the pole if it was placed on top of the tip of the pole. This is the value with which the vertical loading will be compared to and evaluated. The standards will also specify the maximum allowable bending moment measured at the ground line. This is the value with which the horizontal loads will be evaluated. Let's take a look at an example. Let's start with a 50-foot pole, and then we'll attach a 3-phase transformer bank. The standard setting depth of a 50-foot pole is 10% of the pole length plus an additional 2 feet. This gives a setting depth of 7 feet. This results in an above-ground pole height of 43 feet. We'll attach our transformer to a position 35 feet above the ground. Also note that the transformers are mounted so that their center of mass is about 20 inches away from the center of the pole. If we look at this loading triangle, we can see that we have a vertical load equal to the weight of the transformer bank and the related equipment. We'll assume this to be about 2,250 pounds. And since the transformer is mounted offset from the center of the pole, this also results in a small horizontal load of about 106 pounds. Now, to compare these horizontal and vertical loads to the loading values in the standards, we need to do some converting. We'll start with the horizontal load of 106 pounds. Since this is applied to the pole at a point 35 feet above the ground line, we simply need to multiply 106 pounds by 35 feet to get a result of 3,710 foot-pounds. This is our bending moment evaluated at the ground line. We then need to convert our vertical load of 2,250 pounds to a pole tip equivalent load. This is a little tricky. Most pole loading software programs do something similar automatically. Since our transformers are attached at a point on the pole where the diameter of the pole is much larger than it is at the pole tip, we need to convert this load to an equivalent load, assuming the weight was applied to the pole tip. In this case, I'm going to use a conversion factor of about 0.65 found in one of my standards manuals. This gives a pole tip equivalent load of about 1,451 pounds. Now we can compare our loading values to those given in the standards. We can see that both our vertical load, evaluated at the pole tip, and our bending moment, evaluated at the ground line, fall well within the limits of our Class 5 pole. So far, so good. Most pole loading due to the weight of equipment can be determined in a similar manner. Let's look at another example that includes the weight of the conductors attached to the pole. When the conductors are strung across our pole in a straight line, as shown in this top-down view, and they're connected to the pole with standard tie-top insulators, this is called a tangent pole. A tangent pole is one in which the conductors are not dead-ended on the crossarm, and they also don't form any kind of line angle. We'll talk more about dead-end poles and line angles in just a moment. On a tangent pole, the only load applied to the pole as a result of the conductors is generally just the weight of the conductors and the associated crossarms. In our example, we have double crossarms and 4 conductors that are symmetrically loading the pole above its center axis. So all of the conductor load is vertical in nature with no horizontal load. The vertical load is determined by calculating the weight of the conductors of 1/2 of each of the adjacent spans. So if we have a 200-foot span on the left and a 300-foot span on the right, our loading span would include 100 feet of the span on the left and 150 feet of the span on the right. Our loading span would then be this 250-foot length of 4 conductors. If we assume the conductor size to be 336 ACSR with a weight of about 439 pounds per 1,000 feet, our conductor weight would be exactly that, 439 pounds, since our loading span is 250 feet with 4 conductors. We would also include the weight of the crossarms and other equipment, which I'll estimate to be about 200 pounds. We would have an additional vertical load on the pole of 639 pounds as a result of the conductors. And since our crossarm is attached about 1 foot below the tip of the pole, we need to convert that vertical load to a pole tip equivalent. I'm going to do that by multiplying 639 pounds by a conversion factor of 0.93 to get a final pole tip load of about 594 pounds. If we add the 594-pound pole tip vertical load to our pole, we end up with a total vertical load, including our transformer bank, of 2,045 pounds. And as you can see, this exceeds the maximum allowable pole tip load of our Class 5 pole. So for this type of construction, a Class 5 pole would definitely be out. We would need to use, at minimum, a Class 3 pole for this type of application. This is a tangent pole, and I mentioned that on tangent poles, the conductors don't create any line angles. You can see that here. The conductors are strung straight through from pole to pole without any change in direction. This is an angle pole. Because the conductors are strung on this pole in one continuous run, you may hear a line worker refer to this as a running corner pole. Unlike tangent poles, where the load on the pole is a result of the conductor weight, the load on this pole is caused by the conductor tension. It's also not a vertical load. It's a horizontal load in the transverse direction. For example, if we assume the conductors are number 2 AWAC with a tension of 1,200 pounds each, we end up with a total tension of about 4,800 pounds in each direction. If the conductors make a line angle of 10 degrees, as shown, the resultant transverse load will be about 1,667 pounds. If this is applied to our 50-foot pole, 43 feet above the ground line, it would result in a bending moment of over 71,000 foot-pounds. This bending moment of 71,000 foot-pounds exceeds the limits of both our Class 5 and Class 3 poles. You might think that we would just need to use the Class 1 pole and everything would be good. Let me explain why that's not the case. When a horizontal load is applied to a wood pole, this causes the pole to bend. This is called deflection. Deflection isn't necessarily a bad thing. In fact, it allows wood poles to flex a little on windy days to absorb the high horizontal loads from wind. However, if left unchecked, permanent deflection can cause some issues. This is a small, unguyed service pole. You can see the service conductors attached at the top of the pole applying a horizontal load, which is pulling the pole to the right. If I add this vertical line for comparison, you can see the deflection become more apparent. The permanent deflection is causing the wood fibers on the right side of the pole to be under compression, and over time, that compression has caused these giant cracks to form in the pole. Steel poles don't bend and deflect the same way wood poles do. However, when unchecked horizontal loads are applied to steel poles, over time they can start to lean into the load as the soil foundation gives way. Because of the tendency of overhead poles to either deflect or lean, almost all horizontal loads caused by the conductors needs to be counteracted with a guy and an anchor. In this image, you can see a small line angle pulling the pole to the left. This horizontal load is being counteracted by this guy and anchor applying an equal and opposite horizontal force to the other side of the pole. For that reason, angle poles are installed with what's called a bisect anchor. It's called a bisect anchor because it's installed in a location that bisects the line angle right in the middle, and it should be in line or parallel to the crossarm. The purpose of the bisect anchor is to apply a horizontal force equal to and in the opposite direction of our transverse load. In this case, the bisect anchor would need to apply a horizontal load of 1,667 pounds in the direction opposite the load caused by the conductors. To do so, however, does come at a cost. If we install a guy and anchor that can provide 1,667 pounds of horizontal load in the opposite direction of our transverse load, this would effectively cancel out the 71,000 foot-pounds of bending moment on the pole due to the conductor tension. If we chose to install our anchor with a 30-foot lead length from the center of the pole, this would require us to tension the guy wire to a little over 2,800 pounds. When we do so, the guy wire creates a vertical load on the pole of about 2,300 pounds. And when we calculate the equivalent pole tip load, we end up with a vertical load of about 2,139 pounds. This corrects our problem with the bending moment, but creates a new vertical load that exceeds the limit of our Class 5 pole. In fact, guy wires and anchors are the largest cause of vertical loading on utility poles. When a guy and anchor are necessary, this usually results in the need for a larger class pole. Let's look at one more example. This is a dead-end pole. You can tell because the conductors are terminated at the pole and don't continue on in the other direction. They're also connected to the crossarm with a special insulator called a suspension insulator, usually referred to as a dead-end insulator. Let's assume the conductors are number 2 ACSR with a combined tension of 2,400 pounds. This time, however, the conductors are pulling in only one direction. If this is our same 50-foot pole, with the conductors attached at a point 42 feet above the ground line, this will create a bending moment of over 100,000 foot-pounds. This bending moment exceeds the limits of all of the poles in our inventory, so we'll need to add a guy and anchor to counteract the horizontal load created by the dead-ended conductors. We need to install a guy and anchor that can offset the horizontal load of 2,400 pounds placed on the pole by the conductors. We'll do this by creating an equal and opposite horizontal load of 2,400 pounds. This will cancel out our bending moment. If we install our anchor with the same lead length of 30 feet, this will require a guy tension of a little more than 4,000 pounds. The guy wire will then create a vertical load on the pole of about 3,300 pounds, which will convert to a pole tip equivalent of 3,105 pounds. This vertical load of 3,100 pounds exceeds the limits of our Class 5 and Class 3 poles. We'll need to use our Class 1 pole for this dead-ended construction. Here's a great image of a dead-end pole and anchor. So far, we've covered the loads on poles caused by equipment like a three-phase transformer bank. The same concept can be used to evaluate any equipment attached to a pole. We've also talked about the loading due to the weight of conductors, and we talked about horizontal loads caused by line angles and dead ends. Most pole loading can be determined with these 4 strategies or by combining them and adding up the resultant loads. For example, this is called a buck pole. It has a tangent line arm on top, supporting 3 conductors. The vertical load caused by these conductors can be determined just by calculating the weight of the loading span and the associated crossarm, just like our example. Just below the line arm is what's called a buck arm. A buck arm allows a branch line to be created by extending another set of conductors in a direction perpendicular to the tangent conductors on top. This buck arm is just a dead-ended arm with a guy and anchor, just like in our example. The total load on the pole can be determined by adding up all of the loads caused by the tangent line arm and the dead-ended buck arm and anchor. You also don't want to forget about these. These are communication lines: telephone, cable TV, and maybe fiber optic. It's always a good practice to select a pole that has sufficient loading capacity to accommodate the addition of communication conductors that might be installed by others. Before we conclude, let me mention a couple of exceptions to what I've said already. On a tangent line, the load on a pole is typically just the conductor weight. That's not always true, however. In mountainous terrain, or areas where the adjacent poles are taller than the target pole, you might end up with a vertical load called uplift. Uplift is caused by the conductor tension applying a vertical load in the upward direction that actually lifts up on the pole. The opposite is also true. When the adjacent poles are lower, this results in something I call a summit load, as if the pole were installed on top of a mountain or a hill. This results in larger than normal vertical loads. Both of these situations need to be accounted for when performing pole loading calculations. You can see both of these loads happening here. The pole on the left is being subjected to some uplift caused by the much taller pole on the right, and the pole on the right is being subjected to some additional summit loading as a result. I also mentioned that almost all horizontal loads applied to poles by conductors need to be offset with a guy and anchor. There are 2 exceptions to this, and this is one of those exceptions. This is an angle pole with a very small line angle. Most utilities allow small line angles to be unguyed as long as the line angle is generally less than about 3 to 5 degrees. The size of the conductor is an important consideration here also. If these were larger conductors, a guy and anchor might be necessary. The second exception is what's called a slack span. A slack span is a very short, low-tension span of conductor that's usually installed slack because there's no physical room for a guy and anchor to be installed. In this case, the property owner where the anchor would need to be installed probably didn't want to grant an easement to the utility. Slack spans are generally allowed in certain situations, but they should be treated with caution. A closer look at the pole on the right will show that it's beginning to lean to the left as a result of the slack span. Stay tuned for part 2, where we talk about the additional loads on poles due to weather. Thanks for watching.